Great. Okay, we are recording. So from last week, we made this wonderful Mule One injector spacer. And so Scott, you were not here.
True, yeah.
However, this is on the GrabCAD. It is in the I believe it's propulsion, and then the propulsion specific, GrabCAD, and then in the Skilldevs. These are all the parts we need. Yeah, you can open it from there. But so I'm just gonna have my libraries crash on me. That's okay. But once we're not going to be getting straight into this just yet, but so that'll give you some time to get your stuff. But we can start moving on through the slides. Wait, am I sharing the wrong screen? Am I sharing the slides right now?
I don't know if I'm added to.
No, you can see my. Okay. Oh, are you not added to the propulsion GrabCAD?
I don't know. I'm on 10K Hayek 2, Hayek 3. I don't know if I'm on.
Oh, you might have to download it from the the workbench, like online, or scroll through the projects on the left side and download. Oh no, downloading all of propulsion. It's not fun. You know what? I think I have an idea. I may be able to just send them to you directly, so you don't have to download the entire propulsion GrabCAD.
I should be able to. Oh, it keeps logging me into the Rocketry GrabCAD account. Guess not. Yeah, maybe this part doesn't need to go in the recording.
That's okay. I'll just tell Chris to cut it out.
Okay. Yeah, I'm on the UVic Rocketry workbench on GrabCAD, the internet page, and I don't see a propulsion folder.
Don't see it. Okay, that's interesting. And you scrolled through the folders on the left side of the desktop app.
I don't know if that was even an option. Yeah, there's just 3.
Oh, does your GrabCAD not look like this?
No, I don't have nearly that many.
Oh, what? Okay, interesting.
I just have 10,000 for rocket.
I might just be able to, as like a super user of the GrabCAD, I may be able to give you access to all of that.
That would be nice. Yeah.
Okay, let me find my good man Scott.
Do you need my email?
I think I just have to select you.
Oh, yeah, I'm already on the workbench.
Yes, Scott Peterson. Am I allowed to? I don't know how to increase your privileges. Oh, add to projects. There we go. Okay, now you have access to all of them, or you should be able to.
Yeah, I just refreshed.
Sweet.
So 01-propulsion.
01-propulsion.
Got it.
There's lots of stuff in there, but I don't know if you can only individually download the Skilldevs folder, because that is all we will need for today.
Yeah, I'm just gonna get the Skilldevs folder.
Sweet.
Oh, well, I got an email for every folder you just added me to.
Oh, I'm so sorry. Okay,
and the commercial off-the-shelf portion. Is there anything in there?
There is stuff in there. However, we don't need it for today.
All right.
And Logan, you have the assembly?
Yep, have the assembly from last time.
Great. Okay. Okay, does that mean we're all ready to go?
Yeah, we can start.
Great. Okay, so these lovely slides were prepared by Morgan Stewart, and we will be diving into the kind of basics of doing some FEA or finite element analysis. What you will learn in slide 2 is single part analysis. We wanted to cover an analysis of an entire assembly. However, we ran into some licensing issues with memory use. So the student version of Solidworks cannot allocate that much memory for doing the computation on the full assembly, which is very sad. However, we still can do the simulation for each part individually. And so just some notes before running any simulations on slide 3. I want to make sure that every single part has a defined material. We went through this a lot last week, but obviously all materials are going to react differently under different loads. That's very important for designing anything mechanical in nature. And so, secondly, you will need to know what loads you're expecting on your parts. You need to know how your parts are located or fixed. And simulation should always, or as when possible, be backed up by like hand calculations to verify your solution. You shouldn't just like blindly trust your FEA simulation just because you just because you were able to place your loads in the correct spot on your 3D model. You may have some crazy some weird geometry that can make these like stress singularities, I think Claire called them, where you just have this like zero or very, very minuscule amount of material, and that just like is a stress concentration that just infinitesimally builds as the amount of load that's applied increases. And so that can skew your results. And obviously, again, like we don't want to blindly trust our simulations. So those should be verified. Yeah. Moving on to slide 4. So the injector spacer. This spacer is for the injector for Mule 1, our first attempt at a student research and developed hybrid engine. And so Mule 1 was supposed to have a maximum thrust of. Oh, do you have a question, Scott?
Yes, I have a question.
Okay, yes.
We're seeing your SolidWorks window, not the slides.
Yes. Oh, that's okay.
Okay.
Yeah, I'm not pointing to anything on the slides. I'm just kind of referencing them. Unless you want to also see the slides. I'm not.
No,
yeah.
Just wanted to make sure that you.
Okay. Great. Thank you. Yes. So the injector spacer is for an engine that was supposed to exert nominally about 1,000 newtons of axial or of thrust, and so that thrust is obviously transferred through the injector that's sitting inside the combustion chamber, and whatever's behind said injector. And so in that case, what's behind the injector is this spacer, and so this spacer will be experiencing 1,000 newtons of axial force, and so for a bit of context, I don't have any cross-sectional views of what our engine looks like. But if you just watch my hands, if this is so we have one end of the injector, one end of the combustion chamber, and the other end of the combustion chamber. We started out with a combustion chamber that was way too long, and so we now have a spacer at the back, and then our injector, and then the rest of our fuel grain, or like our actual combustion chamber, where before we had injector all the way at the end and then fuel grain throughout, just like a regular you would expect from a hybrid engine. But yeah, the funny story, I don't know what happened, but they just decided we needed way too much fuel, and then they're like, wait, this is wrong. And so then we had to shorten it using this spacer. But yeah, history of good design decisions aside, let us get into some simulations. So, as you see on slide 5, you will first need to enable SolidWorks simulations on the SolidWorks add-ins tab. And we're actually going to tackle the post first. So if you're in the assembly, you can access the post by just pressing open part, or you can grab it from your own folder at home. And we're going to do we're going to run a study on this post. And so once we are in simulation on the top tab, everyone was able to get simulation open okay?
Mine is not. Mine's just grayed out.
It's grayed out on the top.
Yep.
And there's no simulation tab
No.
next to it.
No, there isn't.
And that's interesting. Did you download it with the student version of SolidWorks? Did you get all the add-ins?
It's very possible that I didn't. It was a while ago.
Interesting. Okay. I'm not sure why that's not there. You may be able to, with your student license, just like search up SolidWorks simulation add-in and install it like standalone. So if you'd like, you could try that. I'm not sure. Is that the only one that's grayed out?
No, SolidWorks Motion is also. Yeah, so I think I just didn't select some when I initially downloaded.
That sounds like it. So it should be okay. You should be able to just download it individually. Now. All right. Well, we'll continue on, but we'll be slow. And so once we're in simulation, or in the simulations tab, you can see the only option is new study. So we are going to make a new study. Exciting. Yeah. And so we are going to name this study. We're going to name this study something memorable. So in this case, we know that because our injector spacer is being pushed on from one end, that post is going to be in compression. Logan and Scott, you guys have taken statics. You know that this post is going to be in compression. Why didn't you say that? No, but yeah, so we can just label this compression. I'm going to label it compression 2 because there's already been a compression study done on this post. And this is just a static. This is a static study. So there's no fancy fatigue or buckling or frequency loading. It's just like a single static load. And we will press OK. Now, as you can see on the bottom, we can see there is our different studies. I have a study from before when making the slides, but now we're in a new study, which is handling the compression that we're going to be looking at. And so you can see there's a bunch of different attributes here. We have the surface itself. There's connections, fixtures, external loads, mesh, and result options. And so connections are for defining connections. So like springs, bolts, pins, bearings, all of those connections that may come up within an assembly will be seen in connections. If you wanted to do a simulation of just a single part of an assembly, like for instance, in this case, we could be simulating the fastener connection, so like the screw connection on this post. However, the forces coming from the screw are a lot less than the forces coming from our load. So we don't actually need to add anything in the connections. because we will be defining our post actually using fixtures, and you'll see what I mean by that in a second. Scott, how are we doing with downloads?
It's not exactly cooperating, but
Oh
in
no.
SolidWorks, there's SolidWorks Simulation Express, which is, I guess, like the in-house one for people who don't download the actual one.
Oh.
So I'm just going to use that, and it allows you to put in fixtures and forces and things. So
Oh, sweet. Okay, yeah.
I'll be sticking with that.
Awesome. Okay, yeah. I don't know how limited your usage is going to be of the Express, but at least you'll be able to follow along.
Yeah, that's what I used for like the component that we had a simulation for at the CDR.
Oh yes, the little acrylic piece.
Yeah.
Okay, that's perfect.
So it should be able to. We'll see. We'll see.
Great. Okay. So back to simulation. We are so going through just the different components here. Talking about connections. Fixtures are for different, fixturings. So whether something is fixed by, say, a fastener, these are like the simplified versions that you see in Eng 141, or say it's a roller or a hinge. I assume or in that case, you can also use bearings, use bearing connections, but within the fixtures tab. I'm not sure what the difference is, however. And then you have to define your external loads, pretty self-explanatory. And then the mesh. So the mesh is what divides up our geometry, our part here, into a finite number of elements. Who would have thought that we'd have finite elements in finite element analysis? But so yeah, the mesh is quite important when it comes to having accurate and reliable studies. So we'll be talking about that at length. But first, we have to define our fixtures. So moving to slide 7, we're going to right-click fixtures, and that's going to give us a bunch of options for what kind of fixture we can have. And so we want to simply see the compression in this post based on the load that's being exhibited on it. So we can assume that one side of our post is going to be fixed, and then the other side can compress towards the other side. And so we'll select fixed geometry, and then, this face happens to be the closest. And so I'm going to select this not toroidal. It's just a donut face here with the hole through it, but I'm only going to select the face. I don't want to select the inside of the hole or the outside of the post. And then we'll make sure that's a fixed geometry. That means like this is just not going anywhere. This is stuck in all 3 dimensions, or in all 3 directions on our coordinate axes. And so we will then confirm. So look, now we have a bunch of green dots. This is our fixed geometry. Very cool. Now we are going to apply the load. So right-clicking external loads, we are going to select force at the very top. You can also do torque at this using the same submenu. However, all the other different types of forces that can be applied, you'll have to go in and select them from the main, back over here, back in main external loads. As you can see, we have plenty of different types here. Yeah, so force, and then we select the face that force is acting on, so the other end of the post, and the force, the actual value of that force, is going to be 333 or 334 newtons, which is just the 1/3 of that total 1,000 newtons of force. And it's going in the right direction, so we don't have to change anything here. And that is per item is only applies if you've made multiple selections on different faces. Obviously we can't select total because we only have one face. but now we've defined where we are fixed and where we are pushing on. Does anyone have any questions so far? No. Okay, great. Pretty easy stuff. So moving on slide 9, we are going to, as you may have guessed, select or create our mesh. And so right-clicking mesh, we are going to click on create mesh. And so we can set right now setting up our mesh is relatively simple. Basically, we just select the coarseness or the fineness of our mesh, coarser being less accurate, but also less computationally intensive. The finer it is, the potentially more accurate the simulation will be, and much more numbers need to be crunched. So I like to kind of just like field out, just put it right around there on the fine scale. It's not super, or it's less important when we have very simple geometry like this. The actual or like where we are on the coarse versus fine scale. However, when it comes to element size, we'll be able to change that next in the mesh parameters. So if we left click on mesh parameters, you can see we have 3 different types of meshes. And so the standard mesh, I actually brought some lovely examples of how these meshes are created. And so the standard mesh turns our geometry into these little elements. What are these called? These are tetrahedrons, or a D4, if you're familiar with tabletop RPGs. The tetrahedrons are selected in such a way to max or minimize the angles, the interior angles on that tetrahedron. And so keeping all of the elements as close to an aspect ratio of 1. Just because when we have those really large aspect ratio tetrahedrons have these very tiny itty bitty geometries at the end, which, like I mentioned, can create those like stress singularities, basically, where the computer doesn't know what to do and just assumes that like everything's going to break around this single like zero thickness point, basically. And so typically the standard mesh is good for triangular things and square things. But as you probably saw, there are more types of meshes on the side here. We have the curvature-based mesh, which if you click, we get a lot more options. And so what the curvature-based mesh does is, I'll grab my lovely image here. So the curvature-based mesh this is a very useful, or this is much better optimized for sort of more organic shapes, because the element size is dependent on the amount of elements you've defined to fit within a circle. So basically we have this discretized portion of a circle that can be, and the minimum elements with it that can fit within that circle basically dictate the fineness of creating elements around that sort of geometry. And so we don't do, or at least we try to avoid organic shapes when manufacturing things for the machine shop to make. Sometimes it's hard to avoid when we're doing kind of more complicated work, like the fin feet, for instance, from Hayek 2 and Hayek 3 are some pretty complicated geometry, and have a lot of circular sections in them. And so this curvature-based mesh is really good for any like circular, cylindrical, or like organically shaped parts, which can be estimated by a collection of like circles, if that makes sense. Have any questions so far? Cool. Okay. And so then finally, you see we have one more option, we have blended curvature base mesh. And so what the blended curvature base mesh does, or curvature based mesh, is you can see everything is the same in terms of options, except we have this little calculator here. And so this calculator calculates the minimum element size of our part. And so what it does is it finds the minimum radius of curvature from our present geometry. And so based on the smallest radius that it can find in our part, it will create the smallest element. So like one of these elements, from our circle, based on the smallest circle it can find within our geometry. And so we will include that in our calculation. The include minimum element size from mesh control. What that does is whether if the minimum element size from mesh control, so these parameters here that can be set manually, is smaller than the minimum radius of curvature from geometry, then it'll go with this one. It'll go with the minimum element size from mesh control. But if the curvature from geometry is smaller, then it will pick that one. But so if we calculate, it'll run a very quick little doodad and see the minimum element size value is 3.937 times 10 to the negative 9, which is small, basically 0. And so that can come from the fact that we have cones here at the ends of our drilling, which is a bit problematic because we can't quite have a minimum element size of 0. And so I'm just going to double check that. Yeah, so I'm not sure actually why that didn't work, why it gave us such a small value, like such a teeny weeny little value. I guess, maybe, there we go. I think I actually may have just, even though it was run in the slides, you should be able to see, they say we calculated it. However, I don't think it actually worked because like that's a small number and we can't have that. So what we'll do is I think we'll just stick with the fine for some reason, which is fine. That's okay. Like the idea of the blended curvature base mesh is for stuff like this. So we've got like a big circle on the outside around here, and then this small little pip coming out. And so this the mesh has adapted itself to make elements that are proportional to this small little pip, as well as out to the larger disk that is out there. And so why that wasn't working, I'm not quite sure. However, we're just going to say it's fine and keep on going for the sake of time. But yeah, so that is kind of why we would take, that's what the difference between blended and regular curvature based mesh. And so we are going to then, actually, I'm interested to see, because if we calculate the element size and then it tells us 0 and then we press apply, okay, it just doesn't get mad. Okay, never mind. Don't talk to me then, or don't listen to me. It'll just do whatever it wants, even though the mesh size is 0. So if you, so in the mesh, went in here, include minimum radius, calculate, apply, yes, and the mesh is created. So you can see we have a pretty uniform looking nodes all around the outside. Then inside these holes, you can see as well, or on the faces, they get bigger because, those are flat, and there's not much curvature there. And then you can see it gets smaller and smaller as we get closer to these kind of the ends of these cones here, the cones at the end of our drilling bores or our drilling holes. And so you can see, oh my gosh, it just keeps going. That's really good because the smaller our geometry is, the less likely it's going to be messed up by the more likely it's going to be messed up by an oversized element. Because if we have an element that's way bigger than the kind of relative geometry around it, then that's how we get those errors. And so you can see it's scaled nicely to kind of this definite, oh no, I've lost it. It's scaled nicely to this definite point at the end of our hole. This being said, our analysis is very much not on the inside of these holes, but this is still important to know. But now we've got our mesh. This is great. We've divided up our post, and now it's time to run our study. So we're gonna just click run, and your computer should start chooching. So we can see we have results already. Things have happened. So you can see we have a heat map of what's going on. We have a heat map, and each heat map is for every, or is slightly different for every single result that we have. So we have stress, displacement, and strain right now. So the most important ones that we typically look at are stress, and then displacement, which is stress is obviously important for knowing whether the stress you're getting. So around, you can see we're mostly in the blue section. So 5.697 times 10 to the 6 pascals of von Mies stress. That is less than the yield strength of our material, which is over here at which is the arrow is supposed to be somewhere on the scale. It's not even on the scale, which means that's a good sign for the strength of our post. And then the displacement is important for things like a binding. If we have things that are moving while under load, we wouldn't want deformation from that load to maybe catch things and inhibit them from moving. There is one more result that we like, and that can be found using the, looking back through the slides, it looks like in slide 12, we wanted to quickly talk about editing our assembly or editing our results. And so if you right click displacement, for instance, and then, and then we can edit definition. You can see the deformed shape it's all in millimeters, which is fine. But we can actually, or a lot of the times you'll get really strange looking parts. As you can see, here's actually where the front of our post was supposed to be, and our post has compressed this much in the exaggerated view. And so if we go to user defined or true scale, for in this example, we'll use user defined, and we press left click, you can see our post comes back to full length. Do you have any questions about that? Do you mean to slow down or speed up? Logan, you trying to figure it out on your own?
No, I was trying to look if there was actually a visible, if you zoomed in enough, you could see the difference in the actual deformation of the part in the true scale.
Oh, that's actually interesting.
But yeah, I don't think there is.
Yeah, well, you can see it's about 0.01 millimeters, which is pretty small. But you'll see in the next simulation we have some more funky looking displacement. But one more result we enjoy, and Scott, you'll be very familiar with this, the factor of safety, which the factor of safety being the, for anyone who doesn't know, the factor of safety is just the ratio between the yield strength of your material and the maximum load it is supposed to see. And so if you right click results, you can see we can define factor of safety plot. And just for all, I mean, we only have one body, so that's all that matters. And we don't really need an upper limit for the factor of safety. That'll be fine. And so we'll just press OK. And now we get a heat map of the factor of safety. And so it looks like our factor of safety is about 15 or 16, which is a lot. I think it's it was on one of the beginning slides, or actually the end slide, slide number 25. There's a table of some different expected safety factors for different types of loads. And so you can, if you read the table, you can see like static or short-term loads, like an okay safety factor is like 1 to 2.5. For static long-term loads, that would be like 2 to 5. Repeated loads, 5 to 15. Variable changing loads, fatigue loads, impact loads. Those are all there on that table, and those are all consistent, or those all follow the those are supposed to be consistent with Euler's column formula, which is an interesting thing that you should look at, but we don't have time to discuss in depth today. Again, there's a link at the end of the slides, but yeah, so we have our factor of safety. Our factor of safety is over 10, which is basically overkill in most cases. I mean, we can actually see in the top here, we have the factor of safety distribution. The minimum factor of safety is 16, which is pretty cool. And so we can actually, we can actually get a little bit more helpful information out of these results. If we go back into the stress really quickly, you can see if we right click and then go back to edit definition again, we can actually, and then move over to chart options. So that's just in the second tab of the stress plot definition. We can show the maximum stress. So the point at which maximum stress is being applied. Maximum being 1.735 times 10 to the 7 pascals, which is an amount I can't quite remember because I have my thing in scientific notation. But if I go floating, there we go. So it's that many pascals. So 17 kilopascals. No, megapascals. Yeah. Megapascals. But yeah, so that's good to know. You want to know where the maximum amount of load is acting upon, and you can kind of see that, like, based on that, based on where your maximum load is, you can always, that can be a good point of optimization. Like you could that can kind of tell you where you can where material should stay and where you can maybe subtract material for like weight saving purposes, for instance. But yeah, so that's a handy little detail. And if you want it to stay on your plot, you could just agree to the stress plot there. Actually, one thing I forgot to point out is that once we, just like I sort of predicted, if we show the max and find out where it is, you can see it's right at the tip of the drill. Kind of like we anticipated, because we have that there. We have this convergence into a zero thickness geometry, and so that will most likely be that will continue to be the maximum amount of, or the maximum stress concentration on our part. However, that part, or that piece of our post, is not actually being loaded at all. That's just because our geometry is unfavorable for stress concentration during FEA. However, thankfully, that is again, that's none of that, or all the loading that we are anticipating being on these faces is right around the blue section, so the bottom, or the bottom of our little heat map here, which is nice. That is good. Any questions so far? No, great. Okay, yeah, so this is pretty simple. Excuse me. And so we can see that in terms of actual analysis, we can see that we pass all of these tests because, well, our maximum stress is less than the yield strength. Our factor of safety is well over, like standard is 1.5 for a lot of the things we do. We are well over that by a magnitude of 10. And in terms of displacement, again, 0.01 millimeters is honestly like larger than a lot of the machining tolerances that that we do in the machine shop. So looking pretty good there. Let us move on to the fin ring because, or sorry, not the fin ring, the end ring, because that's slightly more fun. Does anyone have any questions before we move on from the post? No. Okay, great. Oh, excuse me. I'll just open up the fin ring, or sorry, the end ring here, just from the assembly. And now we're gonna do some handy dandy simulations. Before we do that though, we're going to draw a little sketch. And so what that sketch is doing, as you can see on slide 15, we're going to draw a sketch on the front plane. And this sketch is supposed to outline I think it was upside down. There we go. The sketch is supposed to outline the area of contact that the post is making with this ring. And so what we'll do is we'll just add a circle for every single post here. And then we'll just make them all equal. I could have done a pattern within this sketch. However, that's a lot of work. And so the diameter of our posts was 0.375. So now there's the contact area between the posts and the end ring. When we exit this sketch, we're going to name it split because you'll see in a second that we're going to be using this sketch to alter our mesh a bit, or not alter our mesh, but define our loading. And so moving on to slide 16, if we go to the study tab, after opening our new study, we'll name this compression as well. Yoink. What we're going to do is for fixed geometry, we are going to right click and get into fixed geometry. And then we're going to see the split tab here, just beside type. And then what we're going to do is we're going to select our sketch, our split sketch, and for the project sketch. And then the face we're going to be splitting into multiple faces is this front face here, as you can see. And so once we accept that, and I believe that's all we have to do. We don't want single direction. We don't want reverse direction selected. We just need those sketches. We will, oh no. Oh, the selection, it says the selected face has not been split, but we obviously want to split it. So let's do that. Woo, okay. Now you can see it split the face. So now if we select this face, we only get around the outside. And then if we select this one here, we have specific holding on that area, which is exactly what we'd like. And so now we can go and select all three of those faces, and now that is our new fixed point. So imagining that we're pressing against the opposite side of this end ring, it's going to be pressing against the posts, which are our fixture points.
Okay.
Cool. Okay. So how did that go for everybody? Was the splitting okay?
Just trying to catch up.
Oh yeah, sure. Again, if you have any questions or need to catch up, feel free to just yell at me. There's not too many people waiting today.
Yep. And the split feature is not one of the things that is offered in the in-house one.
Oh no. Okay.
So what I did is I did the sketch of the circle of the contact area and then extruded it a little bit.
Oh,
and
sneaky.
I'll apply it to that face.
Wait, so you might also be able to get away with this using SolidWorks. It's like regular SolidWorks. So if you actually go back to your model, and I'll just suppress this split line for a sec. You can actually split this face using the design tools. And so if you can make a sketch again, so basically the same thing we did before, for all of these.
Oops.
Come on.
What did I? Oh, whoops! I put the sketch on the wrong side.
Oh no. Yeah, so we made our same sketch here, but now, Scott, I think what you can do is in features, you can go into curves and then split line. And then is this available in, this is available in your SolidWorks, right?
Yes. Yeah.
Okay, great. Yeah, so you can do split line and then select that sketch and this and the face. And then you want in the projection type of split.
Yeah, that makes a difference.
Yeah, and so now, you got the same thing, but we've done it in our model instead of in the simulation or in the simulation. The one thing this does, it will break mates in assemblies if you do this, and so that being said, I don't know if that also occurs, because it seems like it stores it as the same type of feature in the design tree after you do it in the assembly itself, or sorry, in the study itself. So it might break either way. That's just one thing to be aware of. If anything's made it to that face, it'll throw you an error. But so now I'm actually just going to fix this definition. I see it's okay. So there's no split now, but I'm going into this with these faces already defined. And so I'll just click those. And Scott, does that work for you?
Yep.
Sweet. So yeah, now we have our 3 post contacts being our fixtures. How's that going, Logan?
I think I had to redo the sketch, but
oh, it was on the wrong side.
Yeah.
If you, because you did the sketch over here in just your model view, right?
Mm-hmm.
You should be able to, in the sketch. So this is like the original split, right?
Mm-hmm.
Should be able to click on the drop-down menu, right click on your sketch, and then edit the sketch plane. So right here, and then you can select a different face for that sketch to go on, and that might fix your problem.
Okay, that'd probably work. Okay. Geometry split.
Doing okay over there?
I am confused. Oh. Wait, am I in Sketch?
Do you want to share your screen? Maybe we can help you out. I'll give you sharing privileges. Okay, you may share. Okay, so back in model.
Model?
Oh yeah, in the bottom left-hand corner. Yeah, so you have your split line in the design tree.
Mm-hmm.
And that looks like it's on the right. Can you right click the sketch and then just open in the top left of this menu? Yeah, edit sketch.
Oh, it's on the right side now. Okay.
Yeah, that looks good to me.
Okay.
So, and then you can get rid of that other sketch. So, but there is no split line. Oh, that's because you selected, or you're still splitting the other side. And so if you right click split line, go into edit the feature.
Edit feature.
And now click the other face, so the back face instead. And so, yeah, there we go.
Okay.
All right, that looks good. Okay, now we're back. We're all back up to the same spot.
Okay, thank you.
No problem. Okay, back to it. Okay, so we've got our split line. We back in our study over here. Yeah, so you should just be able to either edit your fixed or just make new fixed geometry.
So it would be split line again, wouldn't it?
So in fixed.
Mm-hmm.
So if because you had it open, did you have it open already? Are you here right now?
I am in that menu, but I will be in the menu. Okay, so I'm in that menu, but I don't have any faces selected.
Okay, that's fine. So you should just be able to select the three split lines.
Oh, okay.
Yeah, the split in the fixturing, this split menu is only for like making splits.
Okay.
But then we'll so now your screen looks like my screen.
Mm-hmm.
Sweet. Okay, now we are finally on to adding our external loads. So we'll be adding a force again. And that's just going to be on the other side of our ring. And so that's going to be 1,000 newtons.
That's a lot of newtons.
That is a lot of newtons. And that's all that will be applied to that face. And now we will go along and create our mesh. Oh, great mesh. And we're going to make this one extra fine. And we'll use blended curvature based mesh again. And we'll see if we can get a actually normal curvature size geometry. Okay, this makes a lot more sense. This is an actual number now. This is good. And so, yeah, I went into blended curvature based mesh. I calculated the minimum element size, and I will apply that. I would love to. Great. So, and you can see the minimum element size is actually bigger than the element size we initially had. But the thing is, that's the smallest element size we need, because that's how small our features are, which is great. That is good. And then, but it looks like Morgan has actually just like not done that and then just made it fine again.
Oh.
But I think to do a bit of an experiment, I think we should go with this blended curvature based mesh. Give it the minimum element size we need, and then have it work from there. Because at that point, like this is just extra simulator, extra computation work that doesn't need to be done, because our results won't get any more accurate than that. Oh, never mind. Okay, he just wants us to ignore it. Never mind. Don't listen to me. We're just gonna listen to the slides and we're gonna make our mesh as fine as possible because Morgan said so. Either way, I don't think it's super necessary. However, just to stay consistent with the slides, we will just have our nice fine mesh at like about 0.01 element size. And then we're going to press mesh. And as long as my computer doesn't crash, you see we have a nice uniform looking mesh here. Looks very nice. It's very good. Yeah, not too much to say about this mesh. Other than that, it is blue. No, now we have our mesh and we're going to run our study. See how long this takes. Oh my God.
Oh, it broke.
What happened to our ring? And you can see in slide 20 of the presentation that we are very shocked that this has happened.
We are in shock.
So shocked. And again, this is just the amplified deformation scale. We can get this out of here by going into edit definition and then getting true scale or user defined scale. Because that was scaled by a factor of 402. So thankfully our fin ring is not going to look like this. And you should just be able to right click it again. And yeah, things have gone back to normal now. That's good.
Simulation. My computer doesn't.
It doesn't what, sorry?
It's still simulating.
Oh. Get a bit of graphics card, nerd.
It's a laptop. What do you want?
Hey man, you purchased that laptop.
No, I didn't.
Oh, that's true. Okay, anyways, you can see we have some interesting looking stress plots, and looks like the most our concentrations are at the corners of our holes here. I guess there's no corners and holes. The edges of our holes, the outermost edges, we have lots of stress. However, we can see that stress, or it's very easy to see where the maximum stress points are, and the maximum stress is about 5.8 times 10 to the 7 pascals. And again, our is well below the yield strength of our lovely 6061 T6 aluminum. And then again, we can do the same thing. We can look at our displacement. Whoa, pretty crazy. It looks like a sad face even. And as well, like we have strain, but we care less about strain. We really care about factor of safety. And so we will also add that to our results. And we have a lovely factor of safety of about 4.7. And again, we can actually, we can add in edit definition, we can also add where is it? Oops, that's not what I wanted. Chart options. Yes. That's in settings or settings or chart options. You can do the maximum and minimum. You can see. In terms of safety factor, the most important is the minimum safety factor. And even then you can see that is the amount of load required before buckling, before deformation. Or like, what's the word? for yielding. Aha, yes. That is the however, like even then the for this section of our for this section of our fin ring to yield first is very, I mean, it's pretty inconsequential thinking about how the back of our fin ring is contained by our posts, and the outside of our, sorry, I keep saying fin ring, of our end ring, and the outside of our end ring is being held by our combustion chamber. Even with a very high safety factor of 4.7, even then we still have, or there's plenty of things to consider that make it even safer still. But yeah, and you can see as again we've passed all of our our kind of basic kind of sanity check tests for these results, as in our yield stress being lower than our maximum stress, and our factor of safety being greater than 1, basically. And deformation, we didn't quite check that. This is exaggerated, but again, it's about 0.002 millimeters now. So again, honestly, like hot or smaller than most of the tolerances that we work in at the machine shop. So pretty inconsequential, which is good to know. So yeah, that is, I think that's almost everything. I think, oh yes, and so that's the stresses put on the end ring. For the stresses on the mid ring, you can see the results in slide 22. And in that case, we just fixed one side of the holes, or of like from the post contact. Here, maybe I'll open the assembly better. Yeah, no. We just had our force acting in the area on one of the posts, and the fixture being on the area of the other post. And you can see we had similar results in the slides there of actually an even higher safety factor of 11. Interesting. Pretty high. But yeah, and so that was those would have been run with the exact same the exact same method, just with different areas. And so you can see in slide 23, this is what was happening with the assembly FEA, insufficient memory, and things getting mad at us. So that will be, sadly, it has to be left as an exercise of the reader. I don't know if we'll be able to like create useful meshes on these assemblies. However, I will hopefully be able to let you guys know if I do, or when I do some more research on that specifically. But there's not enough time to cover it in today's skill dev. Yeah, and then yeah, so say you've tested your design, say you've designed this wonderful injector spacer by chance, and you're still not convinced by the FEA that your injector spacer is going to be strong enough. The next best thing to do, or obviously physical testing is always important and is a surefire way to verify your simulations, but non-destructive or even destructive testing of a structure like this is very helpful, because you could load 1,000 newtons worth of weight on the top and see what happens. We also have like tensile and compressive testing machines available to us at UVic, and so those would also be those are also good resources to use for doing tests like this. But yeah, that concludes our FEA skill dev. Thank you both so much for showing up and hanging out with me for the last hour and 10 minutes.
Thank you for teaching us.
Oh no, Scott, you're muted.
Thanks for setting this up.
Oh, of course, yeah. I mean, honestly, I've it's like studying for these sessions has been a great way for me to learn as well. So yeah, happy to share the knowledge. And yeah, just that last slide there, slide 25 has some of the safety factor standards that we try to work to at UVR. Yeah, that's all. I'll stop the recording. And then